Well, this is fun. I just spent 20 minutes recording the first page and then my computer shut down. So now, and it didn't save it, so I have to start all over. So here is me working through making a key for the sample test. All right, see if I can repeat everything I just did. This says the height as a function of the time is given by this equation. So if I put a time in for t, I get the height. The question is, what are the units? And as when we talked about Galileo, he discovered that the height was 1/2 the acceleration due to gravity times time squared plus the velocity it was thrown at times time plus the height it started at. So this is height at time 0, the velocity at time 0, and the acceleration due to gravity, and it's negative because that's down and the other ones are up, positive. And the acceleration, this is half of the acceleration. So the acceleration is 32, and 32 is the acceleration due to gravity if you're in the English system. 32 feet per second squared. Now, if you're in the metric system, acceleration due to gravity is 9.8 meters per second squared. So if you see 16, which is half of 32, you know this equation is the acceleration due to gravity on Earth in feet and in seconds. So the units for time are feet, and the height, units for height is feet, and the units for time is seconds. Okay? That's what the negative 16 tells us. We are in the English or American units. Okay? So now it says determine h of 1. The height when the time is 1 second. So we're going to do negative 16 times 1 squared plus 40 times 1 plus 10. And I'm in an office where the lights are blinking, and it's driving me nuts, but okay. So 1 squared is 1 times 16. So I got negative 16 plus 40 plus 10. So I got 50 minus 16, which is 34. And that's the height at 1 second. And so the height is in feet. Now, just a side note here, I could have asked you what was the initial speed, and you should have told me it's going 40 feet per second. Or I could have asked you how high was it, and you could say was that 10 feet to start. Okay? Well, here I asked how high was it after 1.5 feet, or 1.5 seconds. So I do negative 16 times 1.5 squared plus 40 times 1.5 plus 10. And that one, we could do it on the calculator. And since I just did this, it should still be there. So there you can see it, and it comes out to be 34 feet. I also did it by typing the equation in here, and I showed several ways to get it. One would be to graph it, and I've changed my screen so that it fits on there. If I just did zoom 6, it goes off the screen. but I can still find the values by going second trace or calculate the value at 1 second, 34. At 1.5 seconds, 34. I could ask for 2 seconds, and it would have been at 26. I could have asked at 3 seconds, and it would have been negative 14. It's gone down below the ground. It's hit the ground and stopped. I could have asked what the domain. But it only makes sense to go from 0 to wherever that is. And I could have found that by saying, calculate the 0. And the 0 is out here somewhere between 2 and 3 seconds. I could say it's between 2 and 3. That's what it means by the bounds. My guess is 2.5 seconds, and it says no, 2.72. That's when it hits the ground. But I didn't ask that yet. I might on the test, might not. I did ask, oh, how do I do those on Desmos? Let's see, let's bring up Desmos. I have it typed in, and I can just move I can enlarge this. Have to do it with a pad because I don't have a touch screen. Oh, come on. I want to know when it's, what did I say? At 1 second. So I'd have to go there, and then this is 1, so I'd follow it up to where it hits the graph. And it looks like it's 32, looks like it's 34. That's 1 second, half a second, 1 second, 1.5 seconds. It looks like it's back down to 34. Okay, that's why we can get 34 twice. It hit 34 on the way up and on the way down. Okay? I can also turn this into a table. Let's see. Let's duplicate this. Let's see. Thought it was that one there. Oh, I forgot. It's not a touch screen. There we go. There, I made a copy of it, and then I can make a table. And here's the values, and I can put in 1.5. And so at 1, it was at 34, and at 1.5, it was 34. Okay? So you can do a table. When's the height? 20. Determine the time in the height at some time is 20. So we got to figure out when the height is 20 feet. So I could set this equal to 20, negative 16t squared plus 40t plus 10 equals 20. And if you remember some algebra, you can subtract 20 and have it equal to 0, and this would be minus 10, subtracting 20 from there. And then you can use the quadratic formula. You might factor some out, or you might be able to factor this. But you could also, on Desmos, you want to know when the height, that question is asking, when is the height 20? Well, it's at this time sideways. It's kind of hard to tell. So if I go up here and type in 20, doesn't do anything. But if I say y equals 20, it draws a graph of 20. And so now I can just click on there, and it says at 2.28 seconds and at 2.218 seconds. 0.282 seconds. It's at 20 feet on the way up, and at 2.218 seconds, it's also at 20 feet on the way down. On the calculator, we could do the same thing. Go to y equals and put in 20, graph. It's off the screen. I need to see higher, so I go to Window, and let's make the high 30. That's over 20, and if I push graph now, there's the ball going up and down, and there's 20 feet, and I can find the intersections. Second, calculate the intersection. It's going to say, oop, I didn't do it. Second, calculate the intersection, 5, enter. And it's asking me, do you want the intersection of this blue curve and something else? And I say, yes. Oh, this red curve, is that the something else? And I say, yes, by pressing enter on both of those. And then it says, guess. So I move close to where I think it is, and it says 2.218, It's at 20. If I want the other one, second, calculate the intersection. And is the blue curve one of the equations? Yes. Is the red one? Yes. And then move close to the other one and press enter, and it says that one is 2.218. That's how you do it on the calculator. Explain the meaning of what you just found. It's the times when the ball is 20 feet high. And if you wanted to add more, the first one is the time when it was going up and 20 feet high, and the second time is when it's on its way down and 20 feet high. Okay? Now this one, what does h, the height, 1.5, at 1.5 seconds, what's the height at 1.5 seconds minus the height at 1 second mean? Well, at 1.5 and in 1 they were both 34, but what it's doing is finding the difference in the heights. How much higher or lower was it at 1.5 than at 1? Difference in heights between 1 second and 1.5 seconds. Okay? Still recording, so I'm okay. Let's go to the next one here. The graph at the right is a graph of the velocities in miles per hour of 2 cars. The red car is the horizontal line, so I'm going to take my red pen and mark that one in red, just to help you. And the blue car is the other line. The vertical axis is in miles per hour, and it's the velocity. The horizontal axis is time in minutes. V of 30, well, V of the time. So 30 is the time, 30 minutes, and V is the velocity, well, that's what this graph is giving us, of the blue car. So at 30 minutes, we go up to the blue car, then over here to figure out how fast it was going, and it looks like it's 35 miles per hour, maybe 36, somewhere around there. Okay. Determine the acceleration. A stands for acceleration. The acceleration at 30 minutes of the blue car. Well, the acceleration is how fast the velocity is changing. Well, that's the slope, is how fast it's changing. So we have to figure out the slope. And when it says to do it at 30, but since this is a straight line, We can do it at 30 or 20 or anywhere on here. The line has always got the same slope. So I'm going to pick 2 points. That one looks like it's 0, 30 miles per hour at time 0. And this point looks like it's at 50 minutes, and it's going 40 miles per hour. And the slope, well, it goes up 10 miles per hour over how much time? What goes from 0 to 50, or 50 minutes. So it increases its speed, it accelerates 10 miles per hour every 50 minutes. If you reduce this, you get 1 mile per 5 minutes. 1 mile per hour faster every 5 minutes. That's pretty hard to do in a car, to hold steadily increasing so that you end up going 1 mile per hour in 5 minutes. That's a slow increase. That would be hard to do, but that's what this graph is saying the blue car did. This says determine D. The D stands for distance. The distance the red car has gone in 30 minutes. Again, that's the time. Distance the red car has gone in 30 minutes. Well, the red car is going 40 miles per hour always. So in 1 hour it would go, in 60 minutes it would go 40 miles. In 30 minutes it would go half of that, 20 miles. Okay? Describe what the intersection of these two lines is. This is the velocity graph, not distance graph. So the intersection of this is the time where both cars are traveling at 40 miles per hour. That time is 50 minutes. Or, if you will, after 50 minutes, both cars are traveling 40 miles per hour. Okay, and I see that that wasn't on the screen, so I'm adjusting that. Okay. Page 2. Well, I noticed when we were doing the make the box with the paper that some of you had trouble reading the ruler. So I said, well, let's test them now, see if they've got it figured out. Over here is centimeters, 28, 29. So here's 1 centimeter, and each mark in there is 1/10 of a centimeter or a millimeter. But I put them over here with the inch side, so you have to use it, because I want to know if you can do the system you guys are raised in here. So these little marks, here's 0, here's 1. How many spaces between marks are there? Well, if you count the spaces, you'll get 16, which means each space is 1/16 of an inch. Now, if we could split this up evenly into 8 pieces, which is here, every 2 marks, then that would be 2/16 or 1/8. And every 4 is 4/16 or 1/4, and 8 is 1/2. So we can count these in 16ths. We want to count the spaces. So 1, 2, 3, 4, 5, 6, 7. I think there are 22 spaces. So that black mark is 22/16 long, or if I count by 8s every 2, 1 pair, 2 pairs, 3 pairs, 4, 5, 6, 7, 8, 9, 10, 11 eighths, which is 22 sixteenths, both divided by 2, 22 sixteenths reduced. 11 eighths inches. You could change it to mixed number. This would be 1 3/8. Or you can change this to 1 6/16 inches. So that, or that, or that. Okay? If you try to do it in quarters, they don't come out evenly. It's not, if you did groups of 4/16, which is a quarter, it doesn't come out to be even. Okay. Now, the paper one. Okay, when we folded the paper, the amount that we folded up on the edge was the key. So if we folded it here and folded there and there and there, that was key because it gets taken away from the width and from the height. So if we fold it where this is 2 3/16, calculate the length. Well, I guess I would call this the length, but you could switch these two if you wanted. The length would be, let's see, it was 17 inches minus 2 of those. So 17, let's see, 2 3/16 plus 2 3/16 is 4 6/16, or 4 3/8 if I reduce this by 2. So if it's 17 long and I take 4 inches off, that makes it 13, and then if I take 3/8 off, it makes it 12 5/8. Okay? The width. So if I take 4 3/8 off of 11, 4 off of 11 is 7, and then remove 3/8 more, I'm at 6 5/8. And the height is whatever that was, 2 3/16. So the volume, and these are all in inches, inches, inches. The volume is length times width times height, these multiplied. And if you do that on a calculator, the way to set that up on a calculator is to do parenthesis 12 plus 5 divided by 8. That's 12 5/8 inches. Parenthesis 6 plus 5 divided by 8. So that's 6 plus 5/8 of an inch more. And times 2 plus 3 divided by 16. And I get 182.96. And I'm multiplying inches by inches, that's area, times another inch is volume. So that's inches times inches times inches, inches cubed. Volume is three-dimensional. That's why it's inches cubed, not inches squared. Okay? Now, if I write a formula for it, using x instead of 2 3/16, well, I got the length by taking 17 minus 2 of those, but I'm calling it x, so minus 2x. 11 minus 2x. And then the height was just whatever the side was, x. That would be the volume in terms of x. Now if I graph that, so I go to y equals clear, clear, and I go up here and I go, I can multiply all this out, but y, if a calculator can handle it, 17 minus 2x. Now I saw some people do 2x minus 17. Well, that would give you a negative answer, but this would also give it a negative answer if you'd switched it around. So it still works, but should do it correctly. 11 minus 2x, and then x. And if I graph, it goes way up, comes down, and goes back up. It goes way up, so I might need to make my window way higher, like maybe 300 for the highest. And there it goes up and down and back up. May want to look a little lower here, so I'll go minus 50. Still goes off. But there's kind of the idea of what the graph looks like. And that's very similar to the one we did for our box. It's just different dimensions in it, so it's going to do similar problem. What's the maximum volume? Well, this is a graph of the volume, so the maximum's up there. Second, calculate the maximum that's somewhere between, let's see, 1 and 4. 1, 4, and I think it's about 2, and it says no, 2.1778. 2.1778. What's the units? Well, that's the x. That's the x. That's in inches. Now, if I go over to here, so I want to delete that one. Forget, not a touch screen. And change this one to, shift parenthesis. I'm trying to do it under the camera here, so it's a little bit challenging. 17 minus 2x, shift, close parenthesis, open parenthesis, 11 minus 2x, close parenthesis, x. And it goes way up. So I'm just going to drag it down some more, drag it down some more. It keeps going up, keeps going up. Haven't got there yet, but it's getting closer. And it says the maximum is 182, 183 at 2.178. 2.178, and the maximum volume was 182.967 cubic inches, or inches to the third, either way. And here you can see that 182.966, and this is pretty much the same number. Okay, round it off. Now it says, what do the x-intercepts? Well, here are x-intercepts. Now, x is the size of the fold up. So 0 would be when we don't fold up anything. That's why we got 0, and it would have no volume. It would also have no volume if we folded it at 1, 2, 3, 4, 5.5. The x-intercepts are 0 inches, 5.5 inches, and the other one is 5, 6, 7, 8, 9.5, 8.5. I can look on here and see the same thing. If I push this way down, so I can see the x, where it crosses the x-axis, that's called x-intercepts. And almost there, here's the x-axis. One's at 0, 0, one's at 5.5, and one's at 8.5. And it's saying 8.5, the volume is 0. 5.5, the volume is 0. At 0, it's 0. Why at 5.5 is it 0? Well, if I take my paper 11 inches wide and fold it exactly in half, half of 11 is 5.5. That's why I'm getting no area, no volume, because I'm folding it in half. The 8.5 is folding it the other way in half. We wouldn't want to do either case. We couldn't do 8.5 because then the 5.5, the 11, 8.5 would be more than half. We can't do that. We can't do the 5. And we wouldn't have a box if we did 0. So the x-intercepts are talking about folding it in places that, in ways that we don't want to do. Folding 11 in half. 17 in half, and no folding at all. Not practical to do any of those. So, when we talk about the main of this, what could x be? Well, if we're going to actually fold a box, we have to be somewhere between 0, can't do 0, we have to be bigger than 0, and in interval notation, and up to 5.5 we could go, but we wouldn't want to go all the way to 5.5 because then we wouldn't have a box. There'd be no bottom. It'd be 0. So there's our domain interval, and the values we get on our graph between 0 and 5.5 are volumes from 0 up to that 182. So we'd get volumes that are something over 0 up to a volume that's approximately 182.967 cubic inches. And I won't be picking whether you put it on this one, whether you put a bracket or parentheses, because this is a rounded off number. This one we know for sure it wouldn't be 0 because we wouldn't fold with 0. Okay, oops, and you can't see that. There we go. There's the domain and there's the range. Okay, page 3. And the thing's still recording, so I'm in good shape here. Okay, so this is a round vase that straight up and down on the side. So as if I pour water in at a constant rate, it goes up at a constant amount. Pretty simple. This one, it's smaller at the bottom than at the top. So at the bottom it's going to raise quickly, and then it's going to slow down as we go up because it's getting wider. This one, it's narrower, getting wider, so it's going to slow down. So it's curving down and for a while, and then it's going to start speeding up, and then at the very end it's going to speed up really fast, filling up that small bit. Okay? Those are pretty straightforward, I hope, for you. Okay. This one, not quite so straightforward. Distance versus time. The car is getting 30 miles per gallon and drives 50 miles per hour. D is the distance, V is the velocity, G is gallons, T is the time. I didn't even have a V in here. G, D, T, I think I got all of them. Okay. If I'm traveling at 50 miles per hour, I can get the distance by just 50 miles in 1 hour. In 2 hours, I go 50 plus 50 is 100. I'd have to take 2 times 50. This is 50 times the amount of hours will give me how far I've gone. The distance based on the gallons. Well, if I get 30 miles per gallon, if I have 1 gallon, I'll go 30 miles. 2 gallons, I'll go 60, so it's just going to be 30 times the gallons. If I want to get gallons from the distance, I have to undo this. This is the inverse of that. So if you were doing what we did, if this looks like y equals 30x, if I switch the y and x, I get x equals 30y, and solve for y, I get x over 30 equals y. So if I give you a distance, let's say 60 miles, the distance, x was the d, I would have to divide it by 30 to find out how many gallons. 60 miles, 30 miles per gallon, I'd take 60 divided by 30 to get 2 gallons to go the 60 miles. And I could do the similar one here. This would turn out to be the distance divided by 50. Hopefully that's clear to you. Play with the numbers on there. Make some sample situations. If I'm driving, if I get 30 miles for every gallon, if I use 2 gallons, I should get 60 miles. So 2 times 30 is 60. If I go 60 miles, if I divide it by 30, I get 2 gallons. So this is how many miles gives you how many gallons. So I have to have the d in the equation. I have to have d in the equation. I have to have g in the equation. I have to have t in the equation. So now I want g of t. That's kind of combining these two numbers. Well, to help us understand that, the variable has to be t. Which one of these has a t? Well, the variable here is a t. So if I do 50t, I give it t, it returns a d. I want to get g. To get g from a d, I have to use this. So I put this in place. This is what d is. 50t is d. So I put this in place of the d, and I get 50t divided by 30 tells me the gallons. Now, if you think about this, if I said 2 hours, 2 times 50 is 100 miles. I take 100 miles, the distance, and divide it by 30, I get the number of gallons. So there's that one. It would be also, if you wanted to, it's g of d of t. That's an example of the use of composition of functions. That's what this is. That. Okay. Final page, page 4. Okay, hopefully I make it through this and the lights don't drive you nuts. Okay, and drive me nuts. Okay, here's F, here's G for these X's, H for those X's, and K is this line for these X's. This height, the heights for those lines. So it says find f of 1. So I'm putting 1 in there. 4 times 1 is 4, minus 3 is 1. So this is g of f of 1 turned out to be 1. So then I got to put 1 into g. So over here, 1 into g comes out to be 0. This says in f and g, put minus 2 and then add your answers. So minus 2 into h, I think I said f, h and g. Minus 2 into h is 1. Minus 2 into g is 3, and so I get 4. This says find the x value where the k value, the height, is 3. So I go over here on k. The height is 3 when the x value is 1. This one says find the g value for 0. The g value for x being 0 is 1. So this turns into h of f of 1, because this g of 0 is 1. So now I got to find f of 1. 1 times 4 is 4, minus 3 is 1. So then I end up with f of 1 turns out to be 1. So I got to find h of 1. So I go to 1, and h is 2 for 1. This says find the inverse for f, for any x. So now we do that, what we said, y equals 4x minus 3, but we want to do it backwards. To the minus 1 means backwards. So we switch the y and x, we get x equals 4y minus 3. And we solve for y, so we add 3. Divide both sides by 4, everything by 4. And so this is f inverse. It's x plus 3 over 4. Let's just check ourselves. If I find f of 2, 2 times 4 is 8 minus 3, I get 5. If I put 5 into the inverse, I should get back to 2. 5 plus 3 is 8, divided by 4 is 2. So it checks. F inverse of 5 turns out to be 2. It works it backwards. What's g inverse? Well, g takes negative 2 and makes it 3, so g inverse would take 3 and make it negative 2. And since I have a table, I'll make a table. It would take 3 and turn it into negative 2. It would take 2 and change it to minus 1. It would take 1 and change it to 0. And it would take 0 and change it to 1. And it would take minus 1 and change it to 2. The inverse will undo g, so everything is backwards. Now h, and here, if possible, is h inverse a function? Well, 1 goes to minus 2, 2 goes to minus 1, but 2 goes to 1. And 1 goes to 2. They have double up, so this is not a function, so it's not possible. And now we got to figure out g inverse of 3. So g would turn a 3 to some, doesn't say what it does, but we're supposed to go backwards, so g of 3 started with a minus 2. So this turns into f of negative 2. G inverse of 3 takes us to minus 2. F of minus 2 is minus 8 minus 3, or negative 11. Okay. And finally, draw the inverse of this. Now, what the inverse does is reverse the points. So let's pick points here. This point is 4, negative 4. This point is 4, negative 4. So if I switch it, I got to go negative 4, 4. So this point gets put up there. This one gets put where? Well, see, that's 1, -3. So I got to go to -3, 1. That point goes to there. So this must go this way. So it's landing on top of itself here. And this is close. This looks like -2.1, -1.9. So if I switch it, this point would go to -1.9, -2.1, which should be here. So this goes almost on top of itself to there. So this ends up there. Now where does this end up? Well, that point would end up over here, so it's going to go like that. Because this point was -4, 4. So it's going to go to 4, -4. So this shape goes to here, and this curl is going to come off of this somehow. So what's this point? Well, that's -7, 5. So I have to go to 5, -7. And that curl comes down like that. Again, we've discovered that it's a reflection over the y = x. Whatever was here gets put over here, and whatever's here gets put over there. And since this was so close to the same in here, they almost land on top of each other. But that's what you want to do. You want to find points on the original, switch them in, and graph those. And it should look like a reflection, like a mirror image over that y = x line. Okay? And that's it.